Hi, I'm Nanak Nihal. I'm one of the co-founders of Human.Tech and Holonym Foundation. So we build cryptography for digital human rights, such as privacy, security, personhood, access to finance. How I got into this space was my co-founder and I were originally building tools that were not private at all. We were building identity for scientists on the blockchain. And we started to get really worried right before our product launch that we were just letting people put this information on a public ledger, because blockchains are all public for the most part. Most blockchains have no privacy. So we were super concerned at what we were about to launch the world, and we decided, let's delay this. Let's study privacy enhancing technologies and then build a better version. And so then we got really deep into privacy. It was really fun learning about these tools. If you're a math nerd or always wanted to learn math like me, but never did, learning cryptography is a great way to dive into that, and really fun challenge to actually build really meaningful tools. I think there's so much to be built with cryptography to enhance privacy that hasn't been explored just because of the sheer complexity of it. But these tools are getting easier and easier to use, and it's becoming more accessible. So now is a really great time to be building privacy preserving applications. And so we got really interested in this, started building more products. And I'm here today to share some tips and stories, obstacles to avoid, help to find a direction and like how to actually get started. And I think the first most important step is decide which tool you want to use. So, there'll always be a hot new word. Like right now, I think FHE is a little hotter than ZK. MPC is not too hot, but really, these things change all the time. So I would look at the different tools and find whichever is best for your particular use case. So ZK, for example, if you're in a situation where you want privacy on, the user can see their data, but you don't want any server to see the data, and you don't want anybody to have to be online all the time, then ZK is really great. So ZK lets you prove any statement about any private data you know. So it's really great for identity. You have an identity, you want to prove that you are over 21 in order to get into a bar, you want to prove you're from a certain list of countries for compliance. This is something ZK is very well suited for. Now, if you want to do something more collaborative, like let's say you want to jointly train a machine learning model with other folks, you want to use MPC perhaps, or FHE. So MPC, the main downside is it requires liveness of every party. MPC is multi-party computation. So multi-party computation, you're going to do computation together with one or more parties. A really great subset of this, worth exploring as well, is two-party computation, because that has a really cool trust model. You can have a computation share between a user and a server. And that way you're not like trusting some network to have all the data. The user always has a share. So two-party computation is great. Also 2PC MPC, which is like the user and a network together make a computation. So yeah, this is very good for situations where, for example, you want to share this computation and you're okay with other parties having to be live for the computation to happen. So the user has to be live, the parties have to be live. Now, if you don't want the user to have to be involved in the computation, let's say it's a really expensive computation, you don't want to run it on the user device, but you want whoever is doing the computation to not have access to the user data, that's where FHE, fully homomorphic encryption, is really helpful. So this is really useful for some machine learning applications as well. User has an input, you want to do some machine learning computation, but the user doing it in ZK is just too expensive on the device. FHE is going to be slower, more expensive, but you can run it on a very, very big server because the server doesn't have to see the user data. Whereas in ZK, whoever's doing the computation has to see the data. So whichever one you choose, just depends on your use case. And it's going to be a very different paradigm in programming. So we're used to programming like programs. These will run, you have instructions, and the CPU will just like jump to certain instructions. They're all compiled down to assembly and then binary, and there's RAM. We're used to this sort of model. And a lot of the concepts we have intuitively when we write code don't apply because this model doesn't apply. So like if statements and for loops and while loops, These will be different when you're working with privacy-enhancing technologies, for the most part, unless you're using enclaves, which is one thing I didn't mention, TEEs. So TEEs are less of a cryptographic innovation, more of a hardware innovation. And TEEs are very, they're more accessible to the standard paradigm of programming. There are some issues in that TEEs are often compromised. They're not secured by math in the same way that cryptography is. And so TEEs get exploited very, very frequently. So it's important to be careful if you're using TEEs. I think TEEs can be a bit easier to develop. But to do TEEs correctly, you have to be aware of stuff like replay attacks, side channel attacks. I'd say these are the two main issues, replay attacks and side channel attacks. So replay attacks, for example, let's say you're building TE. So TEs, they will take a computation and run it in a private environment. So Amazon, Google, Microsoft all support in their cloud services. So AWS, Google Cloud, Azure, they all have this private computation using TEs. And I actually think these are pretty good because they're not, even though they're like decentralized companies, they're not exploited because they have both, really strong hardware and trust assumptions. So that even employees at these organizations will have a very hard time accessing it, and there's never been any breach of these TEs. So I actually counterintuitively do recommend, if you're doing TEs, to do it in a cloud provider like AWS, Azure, or Google Cloud. And yeah, be careful of, if you do it this way, you don't have to be careful of side channel attacks, because side channel attacks, what happens here is that, sure, this computation is private, but let's say you're working with a private key in the TE. Only the TE knows this key, so it's safe. The rest of the device can't see it. The cloud provider can't see it. You can't see it as a developer. But then there's a question of maybe there's a computation that takes slightly longer if one bit in your private key is different. So you can measure the time that this computation takes. You can even measure like the electricity usage of the machine if you have access to the machine, but in this case you don't because it's on a cloud provider. And you can extract information about the private key. You can do like one bit at a time, and after enough computations, you can eventually extract private keys. You can extract secrets. Sometimes people use, rather than timing, they use like a cache access patterns to extract this data. And again, this stuff will only be possible if you're like self-hosting the TE or some untrusted party is hosting the TE. But if it's in a cloud provider, then it's generally better, which I hate to say. But I think this is the way to do TEs. But you still have to be aware of stuff like replay attacks. Replay attacks are where, say you're building private voting application, and it only reveals the vote. So the TE runs its computation, it tallies the votes, gives you the output. But even though TE is isolated, the input to it is not. You're getting the voting inputs from outside. So someone outside can say, okay, let me try to give the votes in a different order. I'll remove this vote, see how that changes the output. Then I'll remove this vote. And then by removing the votes in particular patterns, you can see what the actual votes were. Or at least you can extract a lot of information about the votes because you've just restarted the enclave, run the vote again, and the enclave doesn't know votes are missing. So enclaves also have no persistent storage. So this is another challenge. Like you can't easily have a key that only the enclave knows. There is a technique called key sealing that makes it more possible to do this, but still you have to worry about persistence of information. So with all this in mind, whichever model you choose, whether it's ZK, TEs, FHE, or MPC, there are going to be different paradigms in programming, especially for ZK, MPC, and FHE. You'll have the circuit paradigm. So instead of working in CPU and RAM and the standard things like if statements, for loops, you're actually going to have this predefined circuit. So we're not talking about programs necessarily, we're talking about circuits where you have to have input that satisfies this circuit. You can think of the circuit a little like a program, but it's not dynamic. Like you're not going to be able to jump to different instructions. You're not going to be able to do if statements. You're not going to be able to have a for loop stop on certain conditions. you're going to have to, if you do a for loop, you're going to have every single possible iteration of the for loop. And if you stop somewhere by conditional, the circuit's still going to be as long as possible for loop, because you have to have every step defined in the circuit beforehand. And then there's also this paradigm of public inputs and private inputs, like which inputs can be public, which inputs can be private. These are important to specify because you often want some data public, but you obviously want some data private because we're working with privacy. So for example, maybe you want it to be public, like which government signed your ID. If you're working on a government ID verification program, you need to make public, okay, this is a US government ID and my age is over 18. So that's a public output, but you want to keep the rest private. So you have to define public and private inputs. Now, there are lots of programming languages that have made it easier to build circuits. So for ZK, you have like Noir, Keylung, Circom, and you have stuff like, why am I forgetting the name? Halo 2, you know. So you have all sorts of ways of building circuits, and some are easier than others, like Noir, for example, is doing a really good job actually at being both easy and starting to become pretty performant. There's often going to be a trade-off between ease of use and performance. So you might get the best performance working with Circom and using a custom backend, or maybe like even working some new framework, hand coding your circuits. And you know, with circuit programming, there are also lots of, you know, it's a relatively new space, so don't expect your circuits to be perfectly bug-free. If you're using ZK for a very security-sensitive application, definitely have some backup mechanisms. Like maybe do ZK plus an enclave or something if you're, for example, handling funds based on a circuit, because circuits do get compromised and they're very expensive to audit. One important thing to look at is scalability, because you'll be surprised how soon, once your application takes off, the scalability concerns in the beginning that you may have overlooked or maybe not realized actually become a problem. So we never realized that using a Merkle tree, for example, would lead to scalability issues. So Merkle trees are a common paradigm in ZK identity. Merkle trees are essentially, you can think of it as a way of compressing a set of values. It's called an accumulator. So essentially you have this set of identities, and you prove that you're one of the identities in a set without revealing who you are. And so Merkle trees are a really great way of doing this, a really fun concept. Definitely recommend looking into it if you're building a ZK identity, but be very careful about using them. Because once you have enough users, for example, once we got to about 20,000 users, downloading the Merkle tree and reconstructing it using these expensive cryptographic hashes that are ZK friendly was taking users like 20 minutes, especially in countries like Africa where the devices were not very powerful. So, yeah, scalability is definitely something to look out for. Another important concern to look out for is nullifiers. So nullifiers are what we use. If you're not familiar with nullifiers, nullifiers are used to prevent somebody from doing an action twice in a private way. So the term started with Tornado Cash, where Tornado Cash would, they'd have these notes. So you deposit money and you get this note. This note says, you know, I've deposited this money, and there's a certain key linked with it, and this key is used as a nullifier. So nullifiers prevent you from doing the action twice. So then when you withdraw it, you actually spend this note by revealing the hash of your nullifier. So you're saying, okay, I can never use this nullifier again because it'll hash the same value, and I'm revealing the hash of the nullifier. So that way I can never spend this note again. That prevents you from withdrawing infinite money. You deposit money, you have to make sure it can only be withdrawn once. And with identity, for example, in voting, you want to make sure you can't vote more than once. And if you want to do proof of personhood, prove somebody's like unique person, you want to make sure they can't prove more than once. Even if you want to prove you're over 18 or from a certain country, you want to make sure somebody can't prove this multiple times. You know, or like do the proof, send it to their friend, the friend does a proof who's not in the US or not over 18. Like you have to make sure like one identity leads to one proof. Otherwise, people will abuse the system and let other people who do not have valid identities make other valid proofs. So nullifiers end up being really important. But for identity, it's actually very tricky to make good nullifiers, because you want to have something that, you have to make sure that one identity only leads to one nullifier. So the most straightforward way of doing this is using a centralized database saying, and this is where privacy starts leaking. And actually there's no perfect solution to this. We're working on a solution that can solve it in many use cases, which is a oblivious pseudorandom function. You can check out Human.Network for that, network.human.tech. And this could help making more private nullifiers, depending on your use cases. So nullifiers, if you're working with identity, you want to make sure that a person cannot make multiple nullifiers with their ID. So most straightforward way is centralized database. You store who has verified their identity before, and you make sure that they can only choose one nullifier. If they try it again, you're like, oh, I see in my database this person has done it before, I won't give them a nullifier again. But then there's a privacy leakage here because you know which IDs have verified. And sometimes this is okay, because it's only revealing who has verified, and that might be okay for your level of privacy. I think in most cases this is fine, but sometimes you want to make sure nobody even knows who is registered. So you might think, oh, we can store a hash of the user's nullifier, of the user's identity, instead of storing the actual thing. Well, hashing identity isn't very secure because you can always reverse it. There are not that many identities you can probably brute force very, very quickly. The different names, addresses, phone numbers, whatever that lead to this hash. So with the oblivious pseudorandom function, you can hash in a more secure way where it can't be reversed. And this uses a key of either a decentralized network or a third party that never sees the user's data, but can help the user generate a deterministic key based on their identity data. So this is worth looking into as well. And in case it's helpful, we have Human.Network to help with that. So for building private tools in a hackathon, I would look at existing frameworks that make it really easy to build private apps. For a hackathon, it's gonna be really hard in a short time period to build, fully featured, extremely private, performant app that scales. But you can start with a prototype, and even start with less privacy, but just look at the tech stack and say, hey, I'm going to build this, and make sure the tech stack actually works for what you're going to do. And you can use it to validate the product idea, and then go very deep into the privacy later, make sure it's scalable. And you can also use their frameworks to make it a lot easier to build private apps. Like, for example, I think Noir is not like a huge learning curve. Also, one thing that might be helpful is doing a lot of research before the hackathon. Maybe you just want to start the research at the hackathon, that's cool too. But if you do a lot of research before, you'll be ready to build. There's a lot of planning that goes into a private app because it's not easy to build this stuff. Even if certain programming languages make it easier, you still have to think in a different way when you write the code. So the more research you can do beforehand on the tech stack you might want to use and how to build with that tech stack, whether it's TE, ZK, MPC, FHE, the better. We have this myth right now that's it's three-pronged. One, companies always want to take user data, never care about privacy. Users are fighting this. They don't like that. They really want privacy. And three, those are the three things. Like, one, companies don't want privacy. Two, users do. And three, it's really hard to fix this because the incentives are so strong for collecting user data. I actually think all three of these are somewhat false. There's definitely truth to all of them, but I think, one, companies are more willing to adopt privacy than we think. Two, users are less motivated, but still motivated to act on behalf of their privacy than we think. And three, there's more hope than we might imagine for a more private future. So let's start with companies. why companies actually do care about privacy sometimes. So certainly advertising data and some other types of data are very profitable to collect. And a lot of companies have this as a primary business model, a lot of big companies. But also there are lots of types of data that companies don't want to collect. And you actually see big companies such as Google. Google just released a ZK identity system that they put a lot of work into. Apple has been doing a lot for privacy as well. And Meta has end-to-end encryption in WhatsApp. Now there are lots of improvements they can make in the end-to-end encryption to make it more private. There's and obviously these companies are some of the biggest offenders of privacy as well. But it shows that there are cases where companies do care about privacy. So looking into their motives for doing that might be a good way of finding new avenues to make privacy more popular. Because if these giants see money in privacy, hey, maybe there's actually something that can scale in building private tools. And the other is that there are other types of data that are not an asset to hold or are actually a liability. So for example, social security numbers. I don't think anybody wants to hold social security numbers. You're not going to use them for advertising, but they add a huge risk. You could have a data breach. It's going to look really bad for your company. And it also costs a lot in terms of compliance and cybersecurity to hold this data. So these types of data, this is something where ZK, FHE, all these privacy enhancing technologies can really help companies save money and help users, have their data at a significantly less risk of data breaches. So I think there's some good avenues to increase privacy here. And the other somewhat sad thing is, people think users are very motivated to preserve their privacy, and users do have motivation for that, but the amount is surprisingly small. In our experience, we have two private options of verifying government ID. One is a lot more private than the other, and people choose a less private one because it's easier to do. It's actually more expensive. So there are two options are NFC-enabled passports. So passports is actually, if you're looking for hackathon ideas, there are already projects doing this, but there could be some new interesting takes on what to do with this, because there are these passports that 170 countries support with signed data from the government. And these, you can do a completely private ZK proof of this. Just show, you tap it to your phone, the phone can read it via NFC, and then the phone can do a private computation saying, I am over 18 and doing a ZK proof of that, or I'm from a certain list of countries. So we support this option. And that's completely free because there's no third party involved. You just need to tap it on your phone. Now for people who don't have these passports or don't want to download a mobile app, because sadly web browsers don't yet support web NFC to the extent it's necessary to read these, so you have to download a mobile app. The UX is worse. So for other folks, we also offer the option to just verify in your web browser. Scan your ID with the third party, a standard Web 2 ID verification service. Do the selfie check, and this is it's easier to do because you don't need to download an app, but also we have to pay the third party, so we have to charge for this, and people will still do it, right, because they don't download the app. So it's really important to make sure this balance of cost and benefit is aligned for the user, because users do care. Once web NFC is supported, I think this will be a big unlock because the UX will be on par. I'm sure users will choose the private version any day. If you could use social media without all the advertising, without all your data being shared with all these people, you would definitely do it. But it's just not an option. So making an option, lowering the cost of privacy to the user in terms of friction, money, time, this is a really good way of helping users prioritize their privacy, because they do care, but the cost and benefit is just not aligned for them to actually act on it. So for learning ZK in particular, especially if you want to get into the math of it, I highly recommend, Justin Thaler's book is very comprehensive. And it's a great read. And great reference. Vitalik's blog posts are also quite good. He has a knack for explaining these things in an intuitive way. I also really like Dan Bonnet's ZK whiteboard lectures. I think these are relative. None of this stuff is super accessible as far as the math, but I think they're relatively accessible as a way of learning some of the math behind ZK programming. Any course in cryptography actually is really helpful. Even before diving into a specific technology, whether it's like MPC, FHE, ZK, TEs, just learning the cryptography basics. So starting with Diffie-Hellman, RSA, elliptic curves. And there are lots of resources online that have been published over the past decades about these fundamentals. And then once you get a good grasp of elliptic curves, Diffie-Hellman, RSA, some of these signature algorithms like, EDDSA, ECDSA, threshold cryptography, I think these are good starting points. And then these more complex technologies like ZK, MPC, FHE will make a lot more sense. As you learn these things, there will often be math concepts that you might not have learned, like maybe finite fields, abstract algebra, and then you can quickly learn those on the way. So I think definitely starting with an objective of learning one concept, and then when there's a sub-concept you don't know, looking into that. It might take a few months to get all the prerequisites, but I think it's really helpful to learn these building blocks, and then everything will go a lot smoother. You don't necessarily have to learn that in that order. Like you could start with an advanced concept, and then once there's a sub-concept that is unfamiliar, then you can dive into that. Take a break from the more complex thing, dive into the building block, and then once you learn that, go back. I think that's also a valid strategy. That's generally how I like to learn these things. But yeah, there's a lot out there, and don't get overwhelmed. Like, the math seems really complicated, but really the complexity is more in the number of concepts you have to learn rather than the difficulty of the concepts. So you can learn the math, you'll just have to dedicate some time to it. Yeah, I think now is a great time to be building privacy, because there really are starting to be good incentives for companies and maybe even users to value privacy. And the technology is getting to the state where we have all these tools. Like TLS, we use it all the time. Whenever your browser says HTTPS, you're using TLS for privacy. It's the most ubiquitous privacy tool, and it's done so much good. Like, we could be sharing our credit card information in plain text. People would be reading all our emails if it weren't for these basic cryptography primitives like encryption, Diffie-Hellman, etc. And these were invented a really long time ago. But it just took the right moment for them to actually get adopted and to become practical for use. It took some legal battles as well for encryption. Encryption was almost illegal in the US, but luckily it's not. And we see this with current privacy tools now. History is repeating itself. There are legal battles about should privacy be legal with newer tools, especially in finance. And obviously, I think that privacy being legal is very, very important. And sometimes though it's important to convince people this, to show them, hey, look, we used to think the email, encrypted email was a bad idea, or encrypted websites. But now it's saving, it's preventing people from sniffing our credit card data. It's preventing people from snooping on our emails. And it would be ridiculous to say that encrypted emails are enabling like terrorist activities or anything like that. Like, encrypted email is obviously a good thing, but back then it didn't seem like it, right? So it's like that now, and we just have to keep fighting the good fight. And eventually, I think people realize that privacy is super important and a net benefit to society. And we just have to keep building, and we have to keep being activists for privacy.